Now let's look at the somatic motor pathways. Now remember, of course, these are descending pathways, and they will have their upper motor neurons originating somewhere in the brain. And these upper motor neurons will synapse either in brainstem nuclei or in spinal nuclei in the anterior gray horns of the spinal cord. So the first one we're going to look at, the corticospinal pathway, has three divisions to it. It is sometimes called the pyramidal system, as we will see in a little bit. But these three divisions of it are going to be concerned with conscious motor movement. Then we have the medial and lateral pathways that will be concerned with subconscious motor movement, or things that are not really within our conscious control. So when we look at the corticospinal pathway, we will see that we have three divisions of it. We have an anterior and a lateral corticospinal pathway. And both of these have their upper motor neurons originating within the cerebral cortex. Most of them are originating within that primary motor cortex. And these will descend through the cerebral peduncles, and 85% of these fibers will cross over at the decussation of the pyramids at the medulla oblongata. If you remember that, these are descending white matter tracts that are going to be crossing over to the other side, so that the right hemisphere, the upper motor neurons originating there, will cross over to the left side of the body and vice versa. So 85% will basically cross over at the level of the medulla oblongata at the decussation of the pyramids and continue along in the lateral corticospinal pathway, or the lateral corticospinal tract. The other 15% will stay on the same side and descend through what is called the anterior corticospinal tract. And then when they reach the level of the spinal cord that they will target, they will then cross over and target the lower motor neuron nuclei in the anterior gray horn on the opposite side. So these will cross over in that anterior white commissure and innervate these motor nuclei on the opposite side. Now, the medial and lateral pathways will be concerned with subconscious motor movement. The medial pathway will be concerned mainly with controlling the neck, the trunk, and proximal limb muscles, whereas the lateral pathway will be concerned with the distal muscles, fine movement of the upper limbs. Now, one pathway that I did not mention that is usually considered with a corticospinal pathway is the corticobulbar pathway, or the corticobulbar tract. Again, these motor neurons will originate, their upper motor neurons, within the cerebral cortex, and then they will innervate lower motor neurons in cranial nerve nuclei 3, 4, 5, 6, 7, 9, 11, and 12 that will then control the eyes, the face, the jaw muscles, some muscles of the neck, and the pharynx. So let's have a look at where we would see these tracts in the spinal cord. Obviously, we won't see the corticobulbar tract here because that has already ended in the brainstem. But the corticospinal tract, as the pathway, as the name implies, originates in the cortex, and the upper motor neurons are going to synapse somewhere in the spine. So we have our lateral corticospinal tract here, and we have our anterior corticospinal tract here, and it's symmetric, so we have it on the opposite side as well. Now, if we look at our medial and lateral pathways, we will see that we have medial pathways, again, controlling the trunk, the neck, and the proximal limb muscles, and we will have three divisions of it. The reticulospinal tract, which will have its upper motor neurons in the reticular formation. The tectospinal tract, which is going to have its upper motor neurons originating in the tectum of the midbrain. This is where we find our corpora quadrigemini, so that means the superior and inferior colliculi. So you know immediately that these are going to be mediating reflexes to visual and auditory stimuli. Then we have the vestibulospinal tract, whose upper motor neurons will be originating from our cranial nerve nucleus 8, so the vestibular nucleus, which will be right there on the border of the pons and the medulla oblongata, right where cranial nerve 8 comes in. All right, let's look at the corticospinal tract. So here we have our primary motor cortex. Here we have our corona radiata. We have our axons from our primary motor cortex from the upper motor neurons that are originating in here. And these are the motor neurons that have these very large pyramid-shaped cell bodies and are often called pyramidal neurons. So these pyramidal upper motor neurons will send their axons through the corona radiata and then down through the cerebral peduncles. And about 85% of these fibers will cross over at the level of the medulla oblongata at the decussation of the pyramids. And they will continue to travel along the lateral corticospinal tract on the other side, and then they will synapse on their target lower motor neurons in the anterior great horn on that side. Now, the anterior corticospinal tract will have also neurons that are originating in the primary motor cortex, and again it will travel a very similar pathway, except instead of crossing at the level of the pyramids, it will continue on down in the anterior the corticospinal tract. So what will happen then is it will only cross once it gets to the level of the cord that will innervate. So here we see it here, and it then crosses over in that anterior white commissure right here, and it's going to synapse on a lower motor neuron, again in the anterior gray horn of the spinal cord. We have our corticobulbar tract as well, and as you know, these are going to cross over at the level of the brainstem where their brainstem nuclei reside. So they will cross over and they will innervate brainstem nuclei on the opposite side of the body, and that will control skeletal muscles on the opposite side. So once again, these brainstem nuclei are 3, 4, 5, 6, 7, 9, 11, and 12. All right, so as we've said, the corticospinal pathway is going to provide voluntary control over skeletal muscles, and it begins with those pyramidal cells of the primary motor cortex. So we have two reasons that this is sometimes called the pyramidal system, because we have pyramidal cells in the primary motor cortex, and most of them cross at the decussation of the pyramids at the medulla oblongata, so that's a very easy way to remember them. All right, so we've got those three parts, or those three tracts that are involved in the corticospinal pathway. We've already talked about the corticobulbar tract, the lateral and anterior corticospinal tracts. All right, so as we said, the corticobulbar tract, once again, is going to provide conscious control over the muscles, the skeletal muscles that are going to move your eyes, your jaw, your face, some of the muscles of the neck, and the pharynx, which is your throat. Your pharynx is your throat. So they can also descend and innervate some motor centers of the medial and lateral pathways. So these are also brainstem pathways. Most of them are somewhere in the brainstem. And some of these corticobulbar tracts can also innervate motor centers of these two other tracts that are what we call extrapyramidal, because they're not part of the pyramidal system. However, there's a lot of crosstalk between them, and there's a lot of reciprocal information that's passed between them. And they all of these pathways, it's important to note, they all innervate lower motor neurons that will then innervate skeletal muscle. So a lot of them share the same lower motor neuron targets. All right, so we have a lateral corticospinal tract, and that's going to be on the ventral surface of the medulla oblongata. That's going to basically cross at the pyramids and descend on the lateral, in that white matter on the lateral side of the cord, whereas the other one will descend in the medial part of the cord anteriorly. So the anterior corticospinal tract will descend on the medial side, and it will not cross at the level of the pyramids. It will just simply continue down and then cross at the level of the spinal cord that the lower motor neuron that it innervates is located. All right, so one of the things we've talked about earlier, we talked about the sensory homunculus. We also have a motor homunculus, and so what this is once again, it's a map, and a particular area of motor cortex will be responsible for controlling a particular area of the body on the opposite side. So if we were to look at it, it looks something like this. It looks somewhat similar to the one we saw in the sensory cortex. And we see a slightly different arrangement, but basically the parts of the body that we have the finest motor control over have the largest representation within the motor cortex. So once again, the hand is quite large because we use our hands quite a bit, and we have a lot of fine control. So we think about playing the piano or the violin or typing or speaking, for example. We need to use our tongue a lot and our vocal cords, our larynx here. So we're going to need to use these areas a lot, and we are going to have very fine control over them. You don't need as fine a motor control over your arms, for example, or your toes, for example. Most people are not writing with their toes or playing the piano with their toes, although I have seen it done. But typically, we're going to have a much larger representation of the hand in the motor cortex than we are some other body part, like our back, that we don't use to engage in fine motor movements. So the tongue, the hand, they all have very large representations within the motor cortex. So we can see once again the descending pathways here. So remember our corona radiata that descended through the internal capsule. And so that's going to descend then through the cerebral peduncle. You remember that right on the anterior part of the midbrain. And then some of these fibers are going to go off to their brainstem nuclei targets, so their cranial nerve nuclei targets. Some of them will continue down to the pyramids, cross over, and end up in the lateral corticospinal tract. Others will stay on the same side and descend to the level of the cord that they will innervate, cross over at that level of the cord, and innervate their lower motor neurons. All right, now let's talk about the medial and lateral pathways, because these are more involved in subconscious motor control. So we're going to have several centers that are going to issue motor commands to help keep our balance, to react to stimuli, reflex stimuli, and so forth. So we're going to have the medial pathway, as we've said before, will help control gross motor movements of the neck, trunk, proximal limb muscles. And then our lateral pathway, which is going to have its upper motor neurons arising from the red nucleus. If you remember the red nucleus of the brainstem, then you remember that this is going to be where we're going to have some upper motor neurons, and this is going to end mostly, the upper motor neurons are going to end mostly in the cervical spinal cord, and they're going to innervate targets in the anterior gray horns once again, and the lower motor neurons will then control the distal fine motor movements of the upper limbs. All right, so let's look at the medial pathway. So this is going to be important because we have three sets of nuclei. We have our vestibular nuclei that are associated with cranial nerve 8, and these will be bringing information, or I should say these will be reacting on information that has come from the ear. So you have a very complex organ in the ear called the vestibular organ, and it's going to have semicircular canals that will give you information about acceleration, turning, and acceleration, angular acceleration. And then we're going to have some other parts of this that will give you information about linear acceleration and head tilts, gravity, and this kind of thing. And this is very important for balance and equilibrium. And so we have this basically balance organ in the head, in the ear, that is going to send information along the vestibulocochlear nerve to the via cranial nerve 8 to the vestibular nuclei. And the vestibular nuclei will give us information about head position and movement in rotation and acceleration and this kind of thing. So it's quite important because this is going to help us with our posture, and it's going to help us with our ability to right ourselves if we were to fall. So a lot of reflex movements. Then we're going to have the superior and inferior colliculi. So this is the tectospinal tract. This is going to give us information about loud sounds, sudden movement, bright lights, this kind of thing. So these upper motor neurons are going to originate from there, and they're going to synapse on lower motor neurons that will orient us to a stimulus so that we can then assess it. So if there is a sudden movement or a bright light or a sudden sound that warrants our immediate attention, then this is the pathway by which those motor commands will be issued. Finally, we have the reticular formation. And as you recall, this is that loose, dense patchwork of gray matter that extends the length of the brainstem. And this helps mediate states of awareness and this kind of thing. And so the reticular formation is going to be very highly interconnected with a lot of different pathways, and it too is going to regulate our postural tone and this kind of thing. So now that we've had a chance to review in depth the ascending sensory pathways and the descending motor pathways, let's now look at the basal nuclei and the cerebellum. And the basal nuclei, as you'll recall, are those deep gray matter nuclei within the cerebrum that include the caudate, the putamen, and the globus pallidus that are going to be influencing the upper motor neurons. So we're going to see that the basal nuclei will have connections through the thalamus, creating feedback loops that neurons from the thalamus that are innervated by these basal nuclei neurons will project to the premotor area. So the premotor cortex is the area right in front or anterior to the primary motor cortex that is going to plan motor movements before we do them. So the conscious planning of motor movements. So, for example, if I think about playing the piano, then those programs will be running in that premotor area. So if I can think about playing the piano, I'll activate neurons within that premotor area. But then when I actually go down to sit down to play the piano, then those neurons will then direct the activity of the primary motor cortex, and then I will actually execute the program to play the piano. So the basal nuclei will adjust the output of these motor neurons so they can have inhibitory or excitatory outputs. There are two different populations of cells within the basal nuclei, some of which are cholinergic, that is, they release acetylcholine, and the others are GABAergic, they release gamma-aminobutyric acid. And typically, the GABAergic axons are the ones that are coming into play most often. So they're sort of toning down the activity, and the excitatory neurons usually are not active, and they only become active at certain times. So typically when initiating movements and so forth. So for example, in Parkinson's disease, people lose the control of their basal function, or I should say the basal nuclei lose control, and basically these active neurons are on all the time. So our cholinergic neurons are on, and so they're constantly having muscle tension from this lack of release of motor neurons. So basically they're not adjusting the output of the motor neurons the way they should, and basically people who have Parkinson's have a lot of rigidity, and it takes a long time for them to overcome this rigidity brought on by the fact that their basal nuclei are sending excitatory signals all the time. So we have two pathways. We have one pathway that sends a feedback loop through the thalamus to the premotor cortex, and we also have another pathway that synapses on the upper motor neurons of the reticulospinal tract. So the basal nuclei are very important for generating smooth movements and coordinating patterns of movement, so movement patterns, and initiating movement patterns that are already well established, and then stopping those movement patterns. All right, let's look at, for example, as we've said, the basal nuclei provide the background patterns of movement involved in voluntary motor activities, but they also can control some involuntary activities as well, because as we say, they also have some influence over the upper motor neurons of the reticulospinal tract. So now let's look at the cerebellum. The cerebellum is going to receive input from three different pathways. So it's going to receive sensory input from vision, from equilibrium, that is balance, and also from proprioception. And this is going to be extremely important for being able to maintain balance and postural control and make movements smooth and meaningful. The cerebellum will also be receiving input from all the motor pathways, and its job is to select the inputs that you actually need to make the motor movement. So you'll start with far more motor inputs than you actually need, and the cerebellum basically selects the correct motor inputs and has a sort of comparison of the ongoing movement right now compared to what you've done before. So this is why it's very important in motor learning, because when you learn a new movement, you process that through the cerebellum, and it's learning the activity patterns of that new movement. And so when you go to execute that movement again, the cerebellum can compare the desired motor output to what you have done in the past and keep refining it. So one of the things that's important here is, once again, you are taking some motor movement and initiating it through the upper motor neurons, and the cerebellum then can exert control by toning down the motor output so that you're using only the neurons that you need to make the most efficient movement. Otherwise, your movements might be very uncontrolled. So when you think about learning a new movement, so for example, if you take a movement that you know very well, that you've done many times, that you've trained before, and then you execute that movement, then it usually goes very smoothly. But when you think about when you first learned that movement, it may have taken several tries, trial and error, to get it right. And then you could continually fine-tune it over more practice. It will exert top or control over the corticospinal tract as well as the medial and lateral pathways. So it is controlling or exerting top-down influence on motor neurons, upper motor neurons in these pathways, and it's adjusting that motor output to make the movement as smooth and efficient as possible. All right, so we can then look at sort of higher order motor functions. So a lot of what we know, a lot of our learned motor movements, so our procedural memories, our procedural knowledge, is built on a series of patterns. Sometimes we will have very quick reflex patterns that are built in. Some of them are acquired, but then we can build on these patterns that we already know, that are already innate or hardwired, or in some cases added later through acquired training. But in any case, we have these very simple motor programs that can then be combined into more complex programs. So a lot of the most basic programs that, for example, the hand withdrawal reflex, reciprocal inhibition, crossed extensor reflex. All of these things we will see are important for walking, because as you put one foot forward and then the other foot forward and you cycle through this, you're going to have a lot of cycles of crossed extensor reflexes, and you're going to build on these patterns for more complex movements. So a lot of times we will see that our primary motor cortex is going to direct the movement, and then we're going to have a lot of the fine-tuning of the movement as it's going on done by the basal nuclei and the cerebellum. And a lot of times when you think about patterns, even very complex patterns, so if you're a guitarist or a pianist or play a musical instrument and you learn a piece of music, sometimes you can sit down and execute that piece of music without really thinking about it while you're doing it. Your mind may wander off somewhere and the program will continue, because once you've initiated it, then it can continue without too much more input. Although most people do like to pay attention to what they're doing if they're playing a concert, because you don't want to have your mind wander off somewhere and then forget where you are, which has happened before. I've seen it happen. But in any case, you can have less complex motor patterns, even like simply walking or even dancing or other things. So, a lot of these people, for example, Olympic gymnasts and skaters, they will have their entire their routine as a series of these learned motor patterns that they have built from pretty basic patterns that are already laid down in these pathways. So then they build on them, and they build in extremely complex patterns, and then they'll execute their routine as a series of these complex patterns, so that they're concentrating extremely highly on executing these movements as best they can. But a lot of times you can run into over-analysis or overthinking something, and sometimes people have some of their worst performances when they're overthinking motor patterns that they already know very well, and then they're putting an additional input to them, and then they start coming apart. So if you think about some movement that you know very well and you start trying to analyze it and break it down into little pieces, a lot of times you notice that it's a lot harder to execute it.